Okay, so we will finish this variational methods chapter, and basically uh, just what is remaining is just examples, and perhaps one problem on this helium atom, and a little bit of demonstration on what one can do with these excited states. Okay. So here I just post this paper, which I'll also post in Piazza. This is the famous paper that for which roughly known a Nobel Prize. And if you look at the abstract, it just says that it's a it presents a variational ground state and excited state wave function, which explains the basically condensation of two-dimensional electrons gas in a new kind of state of matter. One line, very simple one line abstract. And if you open the paper, I think it's a very short paper because there is not much to say. He just got it, right? So, and later people did numerical, like as exact, asymptotically exact numerics as possible, and tried to show that, found that this is remarkably accurate. So if you look at the paper, you will see that it says the Hamiltonian, then it just writes down the wave function, which is in equation 6, and equation 7, I think he writes down the something else, I think in excited state or something. And basically it's a very short one, two, how much, 3.5 page paper. Okay, so it's a very, not even 3.5 page, a little more than 3 page, which is very really short paper, and it basically nails the problem. It basically completes the problem. It's and this much is enough for a Nobel Prize. So because it's such a powerful solution, nothing is nowhere close to this. Okay. Okay, so there is no other method that can come this close, except numerics, of course, exact numerics, but that's extremely expensive. As I said, you can progress by toiling by inch by very small amount, which is of course often the only way. Or there is a some out of the blue surprise element which somehow solves the problem. So this is one such example. Okay. So last time I talked about one example of, and I hope all of you have worked it out, that particle in a box. And I said that particle in a box has, so for example, I just said that I want to know this ground state. So the ground state must have this form. Right? So there are many ways to estimate this. You could have badly estimated this. So you can try all those things. So I propose this way. So which is a square minus x square, and that brought you, I think, somewhat like some 1%, 1 point. I showed you last time that if you calculate this, you will get 1.3% accurate. And if you make this a parametric, which means you make a to the power lambda minus x to the power lambda, it comes close to 0.3% for lambda equal to 1.72, that you found by minimizing. Okay, so even though it is a wrong estimation, the actual wave function is sin n pi x by a root 2 by a and 0 to a. So, and you can check that what is the overlap between. So this is the actual wave function. So sin n x, so, and this is psi naught. So you can see that this, how good is this? So psi x, psi naught x, and psi naught tilde x. You see that this is order of 0.999 something like that. Okay, so this is remarkably good, and you can try to see that I can alternatively try various other ways to do that. For example, I can try to do this like a triangular function or something else, and they will not be that well performing. So okay, of course this is a toy problem, and here you have some, it's quite easy, it's just a very simple picture, it's quite easy to guess what can happen here, and then you estimate and you can get pretty close. And as you, this problem gets exponentially harder, of course, exponentially in a, not in a colloquial sense, exponentially harder for a when you want to do it for more difficult scenarios. Okay, so now I wanted you to this is one thing you should notice. The variational method is relatively simple, it's relatively simple in this as a problem of this course, because we are doing very simple few parameter, one parameter, two parameter problem, and actually one parameter, not even two parameter, and I am almost always telling you what is the guess. So that is why the actual variational method is quite non-trivial, but the way it is presented to you for the course is very trivial. So actual method where you don't know the guess, you have to decide the guess. You have to find the guess based on various ways, and then you have to do the parametric minimization, which could be another hard problem. You might know, if you have done any sort of minimization, that minimization is a very hard problem. It's a, let's say I have a function of many parameters, so function of x, y, z, many dimensions, and then many parameters, lambda 1, lambda 2, lambda n. So minimizing, finding the minimum of this function is like literally like it could be very difficult. It is like finding needle in a haystack and all. And there are all kind of advanced techniques to do that. That, for example, this is the landscape. Let's say this is I am drawing it as a 1D landscape, but it could be a very high dimensional landscape. So you have to spot the minima here. But it is also possible that the landscape is something like this, which means there are multiple minima, not one minima. So when that happens, then these are like some sort of a glassy landscape. Okay. So how do you find this? How do you spot this point? And of course, you can say I will search everywhere and calculate the f and see where it is small. But it's incredibly difficult if it is a very high dimensional problem. So then there are all kind of advanced techniques of conjugate gradient and all those methods, where you, for example, you look at a point, you see where the gradient is going downward, and you try to go to and search towards that point. So like that, and so on. Like there are various techniques, and there is no guarantee that any of these techniques will work. And these are like some of the finest problems in optimization, in statistical mechanics, linear algebra, computer science, and all those areas. All these problems are appearing. And as I said, so these are the two difficult aspects of variational calculation. First is guessing the initial wave function, and second is minimizing it. Okay. So these two we are not dealing with in this course, but these are the most two difficult things, and that's what makes many modern problems very interesting. Like, for example, my student Krishna is currently working on one such thing. It is basically a projective symmetry group method to guess the best all the possible wave functions that are consistent with that Hamiltonian, with some complicated frustrated magnet spin liquid Hamiltonian. And that's an enormous task already, that you tell what are the all the good guesses, what are the all the good guesses. And by good guess I mean all those cases that doesn't violate any of the symmetry of the Hamiltonian. And that's an enormous task, because if you have many of you are taking solid state physics course, in solid state physics there are like point group symmetries and space group symmetries. Like there is a huge list of symmetries. So you have to find a wave function that respects all those symmetries. There is a deeper reason, physical reason, to understand why it has to respect all the symmetries. But let's say you have to do that, and then that is your starting point. Then there is still the harder part, that is to minimize. So that you have to do, and to see which one of these are correct or closer. You will never know which one is correct, but which one is closest to correct. Okay. So this is another point to be mentioned here. In variational method, there is no way to know. Of course, in this textbook problems, we are checking that what is a better approximation, what is not so good approximation. But actually, there is no way to know that how close you are or how good is your calculation, right? Because you don't know the actual answer. Here you know it. Like here you know, that's why you are calculating 0, 0 overlap. This number is telling you how good, and this number, the actual 0 minus E0 delta, that is also telling you how good you are. But in reality, you don't know this. So there is only one way, that is to say that if your energy is getting lower, as you are calculating, you are making your approximation better and better, your energy is getting lower. And that is also the reason why this is not very easy to say anything about excited state. The only thing you can say, okay, I found two states, so that I'll tell you. I found two states which are orthogonal to each other, and their energies are different, and they have one nodal difference. Of course, in 1D problem that works. IRD, it's very difficult. So then you can say, okay, I have somehow two states. So I will talk about that. Okay. So this is basically everything. There is not much to say here. This is basically the whole thing, this whole story. And it's pretty simple, but it's pretty difficult also, because finding the good guess is the main point here. Okay. Okay, so I said that I will talk about another example. I will not go through the entire calculation. I'll just tell you that what the problem is, and I think the calculation is very easy. That is the helium atom. So what is the helium atom problem? So helium atom problem is I have two atoms, okay, two electrons in an atom. So Z is equal to 2. So this is my nucleus, 2e plus, and there are two electrons, okay. So of course they are not in same orbit, but I am just drawing it just for the sake of demonstration. Okay. So as I mentioned last time that I expect the total energy if I just calculate the total energy as a sum of these individual electrons. So I can treat this problem as a two hydrogen atom problems, like two separate hydrogen atom problems. So then I will get I solve it for each of these electron and add that, and the energy I'll get 108.8 electron volt. Okay. But the actual answer means the one which we know from experiment is minus 78.98. Okay. So then you might wonder that why, of course, there's not much to wonder. You know why the error is. The error is made because of throwing away the fact that these two electrons also has an interaction, also has a Coulomb interaction. So what is the ground state wave function of this E0? Well, that is correspond to E0. That is of course the product wave function, as we learned earlier. So this is psi R1, psi R2. Yeah. There is also another fact also, of course, you have to, when you take it, so right now I'm not taking into account in the spin, but those are, a full rigorous solution will take into account the spin, will take into account of the fact that this is antisymmetric, the total wave function is antisymmetric and all those things. But it is just a crude approximation. So psi R1, the ground state is of this form, z cube by pi a naught cube square root e to the minus z R1 by a. Okay. So now if I estimate, so now this with this ground state, if I estimate the energy correction using perturbation theory, I have to calculate simply this, that psi 100 e square R1 minus R2, this is function of R1, psi 100 R2 d, and all this quantity, that is d3 R1 d3 R2. Okay. So if I do this calculation, I'm not going through the whole calculation. It's just a simple integral, which it's not super simple. It's a bit tricky, and I have given the how to solve the integral in my lecture notes. I'll here just write down the answer. So what do I get? I do get. So notice I used a Z here. So at Z is basically the nucleus charge. So I'm just using that as a generalized parameter, and I'll tell you in a moment why. So I will get 5z by 4 is 0. So if I calculate this number, this is 74.8 electron volt. That is like only 5.3% error. So 5.3% error to this. Okay. So now you might think, okay, this is pretty good, but then you can make it even better by introducing a variational answer. Okay. So what is the variational principle? The variational principle is to consider the physical phenomena of screening effect. And you, as I think some of you mentioned that you are aware about scaling effect, and scaling effect is nothing but the fact that if I have multiple electrons and one individual electron experiences the charge that is not Z, the nucleus charge that is not Z, but a fraction of Z because of the screening by other electrons. Okay, so this is the screening effect. So if I include the screening effect, my psi R1 1 naught naught will be instead Z prime cube pi a naught cube e to the power minus Z prime R1 a naught. Okay. So instead of Z, I have now Z prime. So now you can ask this question that this is now a parameter, okay? And then you can calculate this again, this the full ground, just the ground state energy, one electron, just the ground state energy, this quantity, just with this new wave function. Okay, so let me call it the Z prime wave function, Z prime wave function, and so on. So notice now here there are two parameters now. One is Z, another is Z prime. So Z prime is in H. H is a function of Z because H is the nucleus. It contains the nucleus charge. But psi has another nucleus charge, which is the nucleus charge it experiences. Okay. So if you calculate this with this, the energy you will find is this 2Z prime square minus 4Z prime 5Z prime by 4. This is what you will find. Now I want to minimize. I want to optimize the problem. So if I optimize the problem, I will get by taking first derivative to 0 del E Z prime. Note Z prime is the only quantity that Z is fixed. Z you cannot do anything about. So when you do that, you get Z prime as Z minus 5 by 6. This calculation is shown in my lecture note and in my pre-recorded lecture, so I am not showing it again. It is just a simple 3-4 lines of algebra. So this you plug into your E naught, and your E naught becomes 77.4. Okay, 77.4 electron volt. That is basically 2% error. Okay. So this is remarkably close to the actual result. Oh, sorry, forgot to mention this is the first order correction with variational principle. Of course, this is this quantity. Okay. So this is this first order correction. When you fix it with this variational wave function instead of the original wave function, then you get a 2% error. Okay, so this is basically everything I wanted to tell. Roughly, I wanted to tell about the ground state variational principle. Then there is one more point which I will avoid for now. That instead of doing a ansatz, instead of taking a specific ansatz, why can't we do a full variational principle, a full variational of the all the wave functions or the full spectrum? So that I will that requires a little bit of functional integral. So I will avoid that for now. But rather, what I will talk about is variational method for excited state. So what can you do about the excited state? Earlier I said it's kind of difficult because you never know that whether you got the excited state or you are falling back to the ground state. Because if your energy is going lower, there is a lower bound for the ground state. But well, excited state also has a lower bound, that is the ground state. So you need at least the ground state to say anything about excited states. Okay. So let's say I have the ground state ansatz. So what the ground state ansatz is this. Okay. So the ground state ansatz is bounded at bottom by the E naught, which is the ground state wave function. Okay. Now let us consider a state which is 0, which means this state is orthogonal to ground state, right? So that means it has to be one of the excited states. Which excited state? I don't know that. I want the first excited state. How do I control that? So then it must be bounded by the first excited state. So I expect this to be bounded by, although this is not. Yeah, so any state that is fully orthogonal to the ground state, that must be at least the first excited state, right? So E1 is the energy of that first excited state. Okay, so this is my guiding principle. So now I do the usual thing. So the psi is, now I know that psi 0 is 0. So C naught is 0. So now I have psi. Okay. So then I can prove that psi h psi is definitely is equal to Cn square En. And if I replace En by E1, so then definitely it is greater than that because En, all the states are higher energy. So n equal to 1 to infinity n square. And that is, I can call it equal to, so this thing is also definitely greater than equal to E1. So that means I can, so this is a quantity n equal to 1. Okay, there is a catch here. The catch is yeah, can you see the catch here? Can you see that why this may not be exactly accurate? So what to do about that? This is some factor times E1.
Can you explain this part again? This side one,
Which part?
the summation in CN, that part.
This term.
No, no, this psi equals greater than equal to E1 at part. E1 summations. That,
This.
yeah.
No, I am just replacing En by E1. And all the Ens which is greater than E1 are higher in energy. Right?
Okay.
So this term must be greater than this. Okay.
Okay.
Sir, are you considering the n eigenkette as the eigenkette of the Hamilton?
No. Yeah, n are the eigenkettes of the, or some eigenkette. Or you can say n is basically the eigenkette of the full Hamiltonian. So H, N, N. Okay. So what I can do? So I have a guess. I have a guess psi, right? And I found that guess to be. I took the guess. So let's say I first did some. I somehow know the ground state. Okay. I know the ground state. I want to estimate the first excited state. So I took a state that is orthogonal to the ground state. So now I'm calculating the expectation value. So this can be expanded in terms of the all the states of the problem. Okay. Now notice that this is a guess wave function. This is not an actual wave function. This is a trial wave function. So if it is a trial wave function, it will be just equal to one of the n's, right? But it is not trial. So that's why it can be expanded as a. Okay. Now I know only this much that this is orthogonal to the ground state. So my C0 must be 0. So then I'm rewriting this as CNN, sum of CNN, where n equal to 0 is thrown out. So now I'm calculating this expectation value and I'm getting this to be greater than E1 times this quantity. Okay. But there is the catch. The catch is this is not 1. Right? This quantity is not 1. So what to do about that? You see the problem? This quantity is not 1. So I cannot say this is a this is 1. This is 1. Now, can you see why it is 1? Yeah, I got confused. This is 1. This has to be 1. So that means psi is psi greater equal to U1. Okay, did you understand this?
Is it because psi is orthogonal to ground state?
Yeah, because the C0 is 0. So this is
Okay.
basically sum of Cn square equal to 1.
Okay.
So this has to be greater than 1. So this guarantees me that if I find a wave function, okay, that will be always bounded by E1. Okay. So what the problem here is, we neither know the 0, right? At the best, so we know a 0 tilde. We don't know the 0, right? So what we can find, we can find a psi tilde which is orthogonal to that 0 tilde. Okay. And we can, so that means I can find one wave function which is orthogonal to 0, that, and I cannot guarantee. Now I can keep improving that, and if I come to the lowest, I can say it is kind of close to the fast excited state. But I hope you understand that how vague is this, right? Because there is no way to guarantee, unless you have some way to continuously go down and claim that this is the lowest possible. Okay. So now, but now I can do one more thing. I can still do one more thing. That is why this becomes so tricky. Like the intuition and all are very important here. And if you look at this Laflin's Nobel Prize winning paper, you will see he finds the fast excited state also. So now we exploit symmetry. Now we exploit symmetry. And we say that if psi naught is even or odd, in case of this problem, it is defined for different problems, then psi has to be odd or even, right? We know, we have proved that for 1D problems, the next consecutive wave functions are of opposite parity. Okay, so if I know, for example, simple harmonic oscillator, okay, we know if my ground state is basically psi naught is m omega by pi h bar fourth root e to the power minus m omega square by 2 h bar. So then my fast excited trial wave function must have opposite parity. So the simplest wave function with opposite parity is this. Okay. Now this is lucky guess because we know this is the exact form. So when you execute the calculation with this, you normalize it and execute the calculation. You get by minimizing with this b, you get 3 by 2 h cut omega. So this is exact and accurate, but it is of course not so in most cases. Okay, because for example, you can try this problem, particle in a box. Okay. So the ground state is a to the power lambda minus x to the power lambda. Okay. So you expect that the fast state will have one node and will be of opposite parity. So you can try to think this, the fast state as x into a minus x. Okay. If I just write it in terms of a quadratic function. Okay. So let's not take the lambda, let's take it to be square or some other power. Then you can of course put also this power, because I want this to be 0 here somewhere in the middle. So x minus a by 2 actually. You can say actually this thing will vanish here and these two edges, right? So you can try to think it like that. X minus a by 2, x minus a, something like that. And then you can put some power, lambda, gamma, something like this. So these sort of things you can do. You can use your guesswork that what should be the form. You have to also try to make it orthogonal to the previous one. This may not be orthogonal. So that sort of thing you have to keep trying. That you choose a wave function which has the features that you expect for this wave function, either symmetry wise or by node theorem wise, and then you try to parameterize, then you make parameterize it and try to make it first orthogonal and then minimize it. Okay. So then you can hope that you can get the fast excited state. So this is basically the art of this. As I said also earlier, is more a art than science, that how do you choose the first one, and then everything depends on that. Of course, the parameterization, minimization only make a small difference. It will bring you close, but if you are starting completely off, then it cannot bring you much closer. Okay. So this is basically the whole point of the variational method. And yeah, so that is all about this chapter. Any questions at this point? If not, then we'll move on to discuss something else. Okay, good. So now I will talk about another technique, which is basically again a non-perturbative technique, and it's also a static technique for solving problems which have which are close to, which has a slow variation of potential in space. So this method is called WKB method. So this method is a very easy method actually. So this could have been discussed in quantum mechanics 1 when we are doing particle in a box problem, and many times this is often discussed there. So both of these are very easy methods. So WKB is actually technically easier. When it works, it's much easier because it basically, the idea, the essence of the idea is following. So if I have an arbitrary potential, okay, and the potential is varying very slow in space, slowly varying. Okay. Then you say it is kind of close to a plane wave. A plane wave means, sorry, it's kind of close to a constant potential. It is slowly varying. You can say it's kind of close to a constant potential. Now again, you can ask, of course, slow compared to what? What is the spatial extent I am talking about? So I will show you that it is slow compared to the de Broglie wavelength of a wave particle. If I have a particle has a wave function, that wave function has a de Broglie wavelength. Now, if the fluctuation in the potentials, the spatial fluctuation is small compared to that, you imagine this as a constant potential. Almost slowly varying means almost constant. and then you use the plane wave solution, because if the potential is not varying in space, then it's plane wave, right? This is like a plane wave. But there are a lot of catches in that, like how do you take care of the boundary, how do you take care of scenarios where the potential is varying from one point to another, how to take care of all this boundary between different scenarios, how to take care of all this Okay, can you hear me and see my screen? Hello? Hello? Can you hear me and see my screen?
Yes, sir.
Yes, sir, we can hear.
Okay, it got disconnected for a few seconds. Okay, so now let's say I have this problem. So this problem is smooth here, but there is a boundary, right? Where it is not smooth, where it is suddenly changing. So I can imagine the solution is plane wave like here, plane wave like here, but not at the boundary. So then how do I take care of that boundary? So this is basically the essence of the trick, essence of the idea. And so I would like to emphasize that any non-perturbative methods are enormously difficult, and they are, what we are showing you here, what we are discussing here are extremely small tiny glimpse of these difficult problems, watered down for your level, and such that you don't see the difficulty, but that is because otherwise it's too difficult. Okay, so that is so that's a point I want you to appreciate. Okay, but what, because the variational method, as I said, the most difficult part were guessing and optimizing. Both of them were trivialized because we are doing only 1D problems, 1D simple problems, one particle simple problems. Okay, now here we are discussing again a problem which can be enormously difficult. We have done this particle, all these problem, particle in a box and particle in a well, particle in a barrier, harmonic oscillator, etc. But what if I have an arbitrary potential which doesn't fit into any of those standard shapes? How can I guess that solution? Okay, so that is the whole question, that is the whole point we are trying to attack. Okay, and that I cannot essentially write it down as a perturbation theory either, right? Because perturbation means I have to write it as h naught plus h1. So I have a clean form, like h naught is something I can solve, h1 is a part that I cannot solve. But I give you this potential, right? Then how do you write it in h naught plus h1? There is no way to do that. So then we either have to do variationally or you have to do something else. So thankfully, this something else, the other method exists for this kind of 1D, 2D problems where the potential is smoothly varying compared to all other length scales of the problem. So the essence of the idea is you take it as a close to plane wave solution and do a perturbation around that plane wave form. So that I will tell you in a moment what is that perturbation. And when you do that, you of course run into problem in these kind of barriers, these kind of sharp changes, and then you have to take care of that separately. Okay, this is the whole point. There is nothing more in it, just to technically how to do that. Now this WKB method, this is coming from these three people, Wenzel. You have came across this guy Kramers before because of this Kramers degeneracy, and of course this guy also you came across in solid state physics. This is Brillouin, the Brillouin zones guy. Okay, so they came up with this method in 1926, and as you can see that in 1925 quantum mechanics the Schrodinger equation was formulated, and within 1 year people have came across all these techniques because they realized this cannot be used when the potential has arbitrary shape. But I will also add that this technique was kind of a 1 century old technique compared to that, because this is a technique to solve differential equations, nonlinear differential equation. And this was brought, so this was known for 1 century ago. And there is a mathematician, applied mathematician or physicist, I'm not sure. So he discussed this problem in 1923, like it's kind of revived this problem from the old literature to solve some problems of that time. And basically these three people took this idea from there and developed it for quantum mechanics. Okay, and notice that this is not just a technique, it also gives you physical insights into the problem that has this kind of slowly varying potential. And that is true for all the techniques that we have been learning. Perturbation theory, variational, all of these will give you some physical insights. Like the perturbation theory can tell, it gives you these processes that picturize this kind of expansions. Okay, so similarly here also. So also I would like to add that this is a general technique to solve this nonlinear wave equation problem, and they are used in many contexts like EM wave optics. There it is called aconal approximation. You will find this term again in the scattering chapter here, because many techniques are borrowed from optics, because as you know, technically Schrodinger equation is a wave equation. Although it's a wave equation of the form that is like not optics wave equation, because this is a single derivative, so that's why it's actually like a heat equation. So many techniques are borrowed both from optics and heat transport in solving quantum mechanics problem. So you will find many analogies, and this technique is also used in fluid mechanics. Okay, these are called short wavelength asymptotics. So you will find the idea, essence of this idea in many different contexts. Okay, so what is it for quantum mechanics? What's the conceptual framework? So the conceptual framework is the short wavelength means solving it for h bar going to zero limit. So the semi-classical limit, close to classical. So this kind of solution is valid near the classical limit. Okay, so that is what I would say, and I can tell you immediately why it is so. Because what did I say? This fluctuation has to be smaller than, has to be less sharp than the extent of this wave function. And if h bar is going to zero, then this thing is very small. So that's why this is like a close to classical. Okay, so this is valid. So this method, so WKB valid when lambda, which is equal to h by p, the de Broglie wavelength is small compared to other length scale. This is a useful method to calculate the bound state energy and tunneling potential. So let's now dive into the method and see how it works. So let's consider a slowly varying potential. Sorry. So this is my Schrodinger equation of a slowly varying potential. So let me call it a slowly varying Px. Now notice one thing, that I am saying it very qualitatively. So I said slowly, okay, slowly compared to what? Slowly compared to the length scale of the de Broglie wavelength, right? But we'll give a more precise definition, so don't worry about it. That will come in a form of inequality, a precise mathematical inequality. That what is that? Now notice, if B is constant, then the solution is psi x e to the power ikx, right? Plane wave. But what I'm saying, that if this Vx is so slowly varying, then the solution is still of the form of plane wave, except now this is, so this is my momentum is also space dependent. Okay, and to be very precise, if I plug in this form here, then the px that comes, that px I can say this is 2m e minus px. So this I call as local momentum. Okay, so this is my ansatz. This is my trial solution, and there is nothing very special about it because it's a general form. I could have written this as a generic exponential term, but I have this plane wave interpretation where I'm saying my potential is slowly varying. So effectively, I'm solving a plane wave equation where the effective energy is E minus Vx, and since Vx is so slowly varying, it's almost like a constant. So my plane wave is close to that functional form, but still the momentum dependence is there. Okay? Now let me tell you one more quick point that this is actually analogous to. Okay, so I will not tell that analogous point. Let me go into the full formalism of this to show you what does that mean. Okay, how does this work? And come back to the interpretation later. So let us say for simplicity, I take the psi x. I work with the time dependent, the space dependent part, only the static Schrodinger equation, and take the solution of the form I sigma x by h bar, where sigma x is a complex number. Okay. What did I do? I just got rid of the a and say that this p is a complex number. So p is complex means there will be a part which is number, which is the prefactor, that is the x. Okay. So that's just to simplify the calculation. Instead of working with two functions, px and ax, I now work with one function, which is a complex function. Okay. So this is my equation 2. This is my trial solution. Now plug 2 into 1. Okay. So 2 into 1 means plug this into the Schrodinger equation. And what you get is basically okay. So notice here you might be wondering, if I plug it back, where is the B, where is the E? But I use this equation to get rid of the B and E. So then what I'll get is basically this Px square. Okay. So what did I do so far? I did nothing. I just used a trial solution and converted my original Schrodinger equation, which was a wave function, which was a differential equation of psi x. Now I converted that into differential equation for the phase factor sigma x. Nothing is achieved because it's a nonlinear equation. It's a complicated. It's still a very complicated equation. Okay, so we have not solved anything. Okay, so now let's try to use various guesswork to show that how can I possibly solve it. Okay, so the notice that the term that is making it most difficult is this term. Okay, this is the nonlinear term. So somehow if I say this term is 0, then it's a very simple equation to solve. Then it is basically an equation if my this term is 0. So now how this term can be 0? Okay, so this term can be 0. So I want this term to be 0 such that my equation is this. And then I of course know my wavelength is lambda by h bar by px, and the potential is almost constant. So when that happens, so it can happen in two ways. First, if h bar is 0, the semi-classical limit, okay, or it can happen if vx is almost v0. So it is some slowly varying potential compared to this thing. And slowly varying means what? The first derivative. So what I demand that the first derivative survives, but the second derivative, this IH bar sigma double prime is 0. It's a smooth function such that the rate of change of sigma is not large compared to the rate of the change of sigma is first derivative. The rate of change of sigma is small. Okay, so that is why these are the two scenarios where this thing can go to 0. Okay? And these two are basically equivalent scenario. That's what we will see. So let's assume that. So now I can solve this equation very easily. And what I'll do instead, I'll do a systematic order by order solution, just like perturbation theory. So let us take h bar as small parameter. H bar as small parameter and expand this thing first order, second order, and so on. This is my answer solution. Okay. So now let's put 4 into 3. Okay, so this is a much more systematic way to do this. If you don't like this sketchy argument, at least you should understand this. So again, we are solving the same standard trick. It's a nonlinear differential equation, for which I am assuming a trial solution, and that trial solution is based on this physical argument that at least at h bar going to zero limit, this equation boils down to this equation. So this is, and this, for this I know the solution. This is what I call the sigma naught solution. And then I'm saying at h bar not going to zero, like when h bar is small, I can think of a higher order correction where I include this kind of terms. So this term is now present, and then I want to know what is the solution with h bar. So I do this power series expansion in h bar as with h bar as small parameter, plug it back into this, and do an odd as we did earlier. So it will become an infinite series as h bar, and each of the coefficient of h bar of a particular power of h bar will vanish. So at ordered h bar to the power 0, it is basically what we already know is this square, where sigma naught x is basically plus minus px, okay, where px is 2m e minus p. Okay. So this is basically the classical action. Okay, now when is this valid? Now the question comes is, now you should think about the validity criteria. So let's think of the validity criteria. Validity. So what is the validity criteria? This term has to be small, right? This term has to be smaller than this term, much smaller than this term. So this validity criteria is nothing but this thing, which is basically del x h bar by sigma x sigma, del x sigma. This has to be less than 1. Now we know that what are these quantity. We already know that px is 2 pi h bar by lambda x, and in first order del x sigma is order px. Okay. So if I plug these two information in this equation, what I get 1 by 2 pi del lambda x. So I just converted these equations in terms of lambda. Okay. Sorry, not del x lambda x. This has to be small. So this is my validity criteria, which I can rewrite as simply saying lambda d lambda dx I just multiplied by lambda in both sides, and I got rid of the 2 pi factor. I just said, okay, the 2, if it is less than 1, this is basically like 2 pi. Okay. If you want, you can keep it also. So it's not a big deal. So you can keep the 2 pi as some c. Okay. But the main point is the change in, so what is this physically? So this is change in wavelength over a distance of one wavelength must be small compared to the wavelength. So this, when this is true physically, this is the physical picture. So that means if I have a potential and then there is a wave function, the wave function is getting modified because of the potential, right? Okay. But this modification must be small over one wavelength, over one lambda. So this is basically the point. Now you might say, okay, this is, I am putting the criteria in terms of the solution, but I don't want the criteria in terms of the solution. I want the criteria in terms of the problem. Right? The lambda is a solution. Lambda is a property of the solution, not a property of the Hamiltonian. Right? So I want to convert this into a property of the Hamiltonian. So what do I use? I use the idea that p square x is 2m e minus vx, okay, and take a derivative in both sides. So pp prime m dv dx, dv dx is basically 1 by m pp prime. Okay, this is what I found. So then lambda x dv dx is basically 2 pi h bar. So what do we have here? So lambda means, we have seen that lambda is basically 2 pi h bar by p. So this lambda is replaced by 2 pi h bar by m, and another p that cuts off this p prime, this p. Okay, and this quantity, this p prime is p derivative, that is much smaller than p square by 2. Why? Because this is basically same as the criteria that h cut square del x square sigma is smaller than del x sigma square. So del x sigma is basically p square, and this is basically p prime. Because del x sigma is p, that we know from here. That is what we have seen in the zeroid. Okay. So basically now my criteria becomes lambda x dv dx is less than p square by 2. So now I have converted the problem into a criteria of a Hamiltonian. Right? So basically, I say change in potential. It's basically the same thing what I said before, just written in a more convenient form. Change in potential over lambda x is small compared to kinetic energy. Okay, so this is what is my problem now. Okay, now let's see an example where this is going to be valid and where this is going to be invalid. Okay, so it's very simple to see. So let us say I have this problem. Okay, this problem of potential. So what happens when the particle approaches here? So this is a turning point. If you think of an oscillator, this is the oscillator will move like this, right? So there is a turning point. It stops and comes. Right? So turning point is where the p goes to 0. The px goes to 0, and then lambda x goes to infinity. Okay, so then obviously you can imagine, if my p goes to 0, this quantity cannot be smaller than this, or if you want to think here, this quantity cannot be smaller than this, right? This quantity cannot be smaller than lambda, right? So this kind of problems will start appearing near the turning point, right? So this whole picture fails near the turning point. So then what do I do? And there is a very simple way to demonstrate this. So here the particle is fast, right? Particle is fast in a classical sense when it is here. As it approaches this point, it gets slow. Similarly, as it approaches this point, it gets slow. So let me call this point x1, this point x2, okay? X-axis. Or I can call it B and A as I used in my notes. So this is the classically allowed region. And this is the classically forbidden region. Of course, we know in quantum mechanics, the particle can be in the forbidden region by tunneling. Okay. So now I can estimate this. So near the turning point, I can think this is like a linear equation. This is like a linear slope. So my Vx minus E can be estimated as a Gx minus A with G greater than 0. And I can estimate my P square as 2m E minus Vx 2m. So this is a linear function now, because this is another important point you should just notice. You might find it, okay, suddenly it is something difficult. So in solid state physics, you might have seen this, that sometimes the band structure is like this and the Fermi surface is here, okay, and sometimes the band structure is something like this and the Fermi surface is here, okay. So if this is the case, then you can always estimate the low energy physics to be linear, because if I have a Fermi surface is cutting here, near the Fermi surface, this line, the band structure, if it is cutting, it is almost like a small line segment. It is almost, so even if whatever the arbitrary form it has, you can think it is like a linear. And generally, when you have this kind of a Fermi function, then it is like a k square if it is cosine k. Although this is not always guarantees, there are other variety of form. Omega k to the power z can happen, arbitrary z. But this is generally how do you estimate? It's when you have a line that is cutting a function or near a function, what is the behavior of the function near that line? You have encountered these examples in solid state, right? Did you do parabolic dispersion? You may not have done linear dispersion. That is a little specialized. Are you there? Okay, probably nobody is actually there. Okay. Anyways, so what do we do? So now I want to estimate this and calculate the lambda x. So I can show it very easily. 2 pi h bar by t, 2 pi h bar, 2 mg a minus x. Okay. So now my d lambda dx is basically pi h bar by 2 mg 1 minus 3 by 2. So I can easily see as x goes to a, the d lambda dx is infinity. So that means you are violating this condition. You are violating this condition. So your WKB approximation is not valid. So what next we'll do? We'll go to next order h bar. Okay. So once we go to order h bar, so I think I will do this WKB approximation only up to order h bar, and then I will solve this. Basically, I will show that what kind of what is the structure of the solution that emerges out of that, and then we will do two examples. One is harmonic oscillator, and another is particle in a barrier, and wave. Okay, so yeah, I would just stop just by showing you that what is the first order equation. So you have to solve this equation. Okay, you have to solve this equation with this ansatz. So sorry, sigma is sigma plus h bar by I sigma 1 plus h bar by I sigma 2 plus dot dot. And we have seen that order h0, it was sigma del x sigma naught square t square x. So order h1 will be I h bar del x square sigma naught plus 2 sigma x sigma naught h bar by I del x sigma 1. So basically we have to solve this equation now at the first order, and we will see that the solution we will get is basically minus half log x, and final solution will be up to this order is half log px means root px when it is exponentiated. So this is basically the solution we will get, and we will derive the validity of this expansion as dp dx less than t. So this is up to which I will do, and then of course one can go to higher order, and basically then I will physically interpret and try to show you how this solution works in the context in a generic context, and then in the context of some problem. So this is basically everything for today. That is all I wanted to say. As you see, that is a very easy chapter operationally. Operationally, all you have to do is basically put a plane wave solution, and as long as your validity criteria is there, which means the problem is weakly varying in the potential, then you can just plug. It's just a plug and play, because your solution is a plane wave. A plane wave with px is just 2m minus e, 2m e minus d px. Okay, that's all. Okay, that is all I wanted to say for today. If there is any question, if you are there, first of all, assuming you are okay, probably you are not there, but if you are there, you can ask questions. Else, we can close this class. Okay, that's all then.